Hi everyone, I'm Valentina Biancacci. I'm a PhD student of the University of Padova, and today I'm going to give you some information about GERDA experiment focusing on the background modeling. So thank you for the nice presentation this morning. So I will go very fast for this couple introductory slides. So I just want to highlight a couple of points. Well, experimentally, as we already know, we expect to have a monoenergetic peak for the neutrinoless double decay in the spectrum of the two electrons emitted. That for the case of germanium-76 isotope, it is around 2039 keV. While if we look at the spectrum for the double beta decay with the emission of the two neutrinos, we expect to have a spread spectrum that tends to the Q beta beta. So just looking at this plot, we can understand that we need a very good energy resolution in order to discriminate these the signal from this kind of background, and also a very low background level because this neutrinoless double beta decay is very rare. So GERDA was one of the experiments that was able to achieve these characteristics, was because, as Abby already said, it was an experiment in Gran Sasso laboratory searching for this particular decay using germanium detectors reached in germanium-76 isotope. These germanium detectors were placed in arrays in the liquid argon closet, surrounding them by pure water. And we already saw this plot here. This is the final results that GERDA published in 2020. And I just want to highlight the main point is that we are human. So we don't want to be affected by our sensation. So what we did to do this analysis is just cover the window around the Q beta beta, where we expect to have the signal. So we covered it, we just blind this region, and then we studied all the spectrum. So modeling the background, and then applied all the cuts that we have with coincident signal and so on. After that, we open the window and see what's inside and doing the analysis. So here you can see the final results that we obtained in terms of the background index, the exposure and the sensitivity. And as you can see, the achievements of GERDA also overcome the goals, the previous goals. So we're happy with that. Okay, now focusing on the background modeling, why is it so important to model the background before even applying the cuts? Well, first of all, it is crucial to identify faint signals. And then we want to verify that actually in the region of interest around the Q beta beta, we have what we expected to have, a uniform distribution for the background. And then it will also allow us to measure the half-life of the two neutrino beta decay with the emission of the neutrinos. And finally, it is important also for the future experiments, because if we know the location of the impurities and so the sources of the background, it is also help us to improve the selection of the materials for the future experiments like Legend. So here you can see the plot of the background model for GERDA, and at the lower energies here, well, the neutrino, the double beta decay is dominating, and higher energy we have most of all alphas from potassium 2010, and in the middle we have a lot of peaks and Compton continuous from the material nearby the detectors and also the natural light activity. So what happens at lower energies? Well, we expect to have that the lower energy is dominated by the argon-39. The argon-39 isotope comes from the liquid argon around the detectors. And then we have, of course, other isotopes and again, the double beta decay. So here you can see just the model of the background that for GERDA. that was extrapolated till lower energies. And here in black, the data that we have collected for the last phase of GERDA. So as you can see, there is, there's something left given by the argon 39 that was not included for the background model for GERDA. So, and here you can see the plot of the argon spectrum, the argon 39 spectrum, which is given by two components, one from the betas that comes from the beta decay of the argon 39, and the gammas coming from the Bremsstrahlung. And in this case, this peak is given mostly by the gammas. So why is this important also for legend? Because going to lower energies, legend can perform new signal search, including some beyond standard model search, signal search. Okay, here just an example of what we have for the data. I just decided to separate them regarding the different three kinds of detectors that we have in GERDA. The ICPC here, Abby already talked about them. Then we have the BG, which has the same advantages, characteristics of the ICPC, but they are smaller. And then the coaxial detector, which were the first kind of detector emerging in GERDA. And the only difference, the most important difference that we can observe between these detectors is given by the active volume. So Abby already talked about it, just a quick reminder. The volume of the detectors are not entirely active, but we have a region around the surface where the detector can't see any signal. So what we can have here, just the charge collection efficiency, which is 100% for the active volume, but 0%, just say 0% for the dead layer thickness. And in a real detector, we have also a transition region called transition layer that, as Abby already said, we don't know exactly how to model it. In this kind of analysis that I'm going to present you, we just decide to model it like a linear function, but we introduce other models in the uncertainties. Okay, why I introduced the active volume? Because we realized that actually the argon 39 shape is very affected by the active volume model. Indeed, as you can see here, just changing the value of the FCCD, which is again stands for full charge collection depth, so the entire thickness when the active volume is not active, you can see that the shapes is changed a lot. Or even if we change the DLF, that is the dead layer fraction, so how much of this FCCD is totally dead. So looking at that, we realized that, yeah, maybe the argon 39 is one way to determine, another way to determine the active volume model, moreover than the characterization of the detector that Abby showed. So we did this analysis, building some Monte Carlo PDFs, changing the value of the FCCD and the DLF. So we have a grid of in two dimensions, and we just did an analysis comparing the data with them. And we performed a statistical analysis with using the delta K square for test statistics. And then we performed also some twice Monte Carlo in order to include also the different uncertainties that we have. So in conclusion here, just preliminary results of what we obtained. We noticed that we can reproduce very well the values for the ICPC, the same detectors that we are using for legend. But for the BGs, we had some problems, as I've already mentioned in a question, that the problem was that the BGs were placed in room temperature, and so we detect a growth of the FCCDs. So what here you can see is just a plot of the FCCD that we obtain with the argon 39 and the interpolation of the two characterizations for the BGs first GERDA and before GERDA. And as you can see, the model, the shapes between all the detectors are consistent between each other. But as Abe already said, we have, even in this case, an offset between the values obtained by the argon-39 and the characterizations. So this brings me to my conclusion. Again, GERDA was an experiment searching for the neutrino-less doublet beta decay using germanium-76. And regarding the background model, we are very happy with this background model because it well described the data and it verified that we had just a constant function in the region of interest. And most of all, the results are compatible with the measurements of the material nearby the detectors. Regarding the argon-39, we noticed that it is the main background that we have at lower energies, and it will be also important for future analysis for legend. And we noticed that the argon-39 spectrum is very sensible to the active volume model. So we decided to use it to determine the active volume. And so the next step will be to give more robust results with also the different systematics that we have. And we, of course, have this elephant from the room regarding this offset that we noticed for so many years also in previous GERDA results. That's it. Thank you.
Are there questions? So I see in your backup slides that you have a beautiful comparison of the Legend 200 background and the anticipated Legend 1000 background. And they're across the board, the backgrounds are much lower in Legend 1000. And for some of them, I can understand that this is because of the larger depth. But for instance, the blue ones, the uranium and thorium chain elements, why are those going to be so much lower in Legend 1000? Is that because you will be doing better materials?
Yeah, exactly. Or better materials, and also if I'm not wrong, this plot was considering that here for the Legend 1000 we are not in Gran Sasso laboratory, but Snow Lab. So even considering the radioactivity.
Yeah, that's why I said for some of them I understand that ambient radioactivity will be lower. For instance, the yellow one here that's even explicitly written muon-induced backgrounds are of course much lower than. Yeah, I was just wondering about the uranium and thorium change because these are probably, I assume these are like intrinsic impurities in the materials you are using, right?
Mm-hmm, yeah.
Okay, so better material selection.
Yes,
thank you.
Mm-hmm.
Any further question? Let's take one more question before we get some coffee.
Yeah, so right at the beginning and on slide 2 or so, you showed the spectrum that also Joachim showed us, but this time with, so they were different, or was it free? Sorry. Yeah, but this time also with these gray histograms after PSD cuts. What was that?
Maybe I have a slide in the backup. I hope so. Okay, so yeah, we have different active background tools regarding where the signal appears, and so we apply different coincidence because I mean our signal is as a single site deposition of the energy in one detector. So it means that if we have their coincidence of this signal also in another detector or in the liquid argon or whatever, we can just cut them. And there is also another tool for this background reduction called pulse shape discrimination, PSD, which is we can discriminate different signals that appears in just inside one detector. We can have different signals. So for example, if there is a gamma that deposits in more than 1 point the energy, even in this case, it is called the multi-site events. Even in this case, it is background and we can reject it. Or if we have some alphas, the alphas can cross can deposit the energy only at the P+ contact, which has a very tiny dead layer. So if only in that case, the alphas can cross and deposit the energy of the detector. And this P plus contact is our readout. So it means that for the P plus, we would have a very high current and even charge. So even in this case, we can discriminate our signal that is like that from the P plus an alphas. And it's the same, I mean, the opposite for the betas, that in that case, they have to reach the P plus contact and they would be slow pulses. So with this, looking at this plot and in particular to the current amplitude over the energy, so this observable, we can discriminate this kind of the signals. So we can cut them and just have the signal like single set event.
Thanks.
Okay, let's thank Valentina. All the speakers today and also in the past days, these were very excellent talks. I'm really impressed also with the discussion that was taking place and also going over time now. So let's have now a half an hour coffee break. And yeah, so in the, after the coffee break, we will continue with some exercises that Olga prepared, and you can already pick some of these exercises here if you want to get an impression. And Olga, I think you will maybe give some pointers after the break. Do you want to do you want to go through the exercises right after the break, or do you can also let students just work on them and then we'll come back later?
I mean, let's do the following. After half an hour break, we go half an hour to exercises, and then you have half an hour.
Okay. So let's come back in half an hour here to the lecture room. Yeah. Okay. Coffee arrived?
Yes, everything's great. Just set up.
I was